Right. Oh, yeah. Alright, so I moved the power supply for the turbo speed sensor. The guys found that one of the vacuum lines, or boost lines, to the wastegates was split. So they fixed that. And I'm hoping with those two changes, we'll be able to actually control boost today. So I'm definitely looking forward to that, because controlling boost is a beautiful thing. So let me see. Alright. Alrighty. So I put it there. Oopsie. My mouse isn't working. There we go. Alright. So now I need to go to my configuration, channels, input, go back to my turbo speed sensor, which is, oops, it's under speed, of course. And alright. This is probably going to be a little less than that. Probably going to do a 3 and 3 and see where it starts off at for voltage. Okay. Oh, I need to connect the ECU. That would help, wouldn't it? I also get the beauty of checking the cold start because it hasn't run yet today. So let's see what happens with that once I get connected. Right now, DI7 is at 4.7 volts, so that's probably the 5 volt bus, I'm guessing. We'll find out. Let's start it. What's our coolant temp say? Engine temp 10.1, inlet air temp 11.7. Okay, that's actually something that's interesting. They should be a little closer to that, I would think, considering that they've been sitting here overnight soaking. However, I did turn the fan on, but that would actually typically make the inlet air temp sensor a little colder. So I see a little disparity there. Let's just check that really quick. It's only a degree or so right now, which isn't a big deal. That's the right one. That's what it's supposed to be. Yeah, that's right. So I think it's this one. Definitely not. Oh, engine's dropping more. Okay, I got the fan on it. So the fan's actually blowing on the radiator and on the engine itself, so that's why that's dropping down. Okay, so we're good to go. I see it dropping some more. Alright, let's start this thing. Nice and cold. That's up at 1500 RPM, so can't complain about that. And I'm still on map-based fueling too. I haven't gone to the TMAF yet. So our target's 16. We're running about 1630. Consistently just above that. Now, if we do this, we go to engine functions, go to idle speed control, go to initial position table. Initial position is 9 right now, which is pretty high, and that could explain why the error's constant positive, because it can't push down, because here's 7.4, so I think I've only given it 2 grams per second authority to remove air. So if I drop one of those out, there we go, there's auto coming down. So the way I would check for that is if I go to my closed loop, minimum deviation here, I've given it 2.5, okay? there, but I don't think I gave it 2.5 here. Yeah, 2.14 here. So I bumped this up and to wherever the highest I have in that other map. Otherwise, there's no point in having that other map. Unless you're trying to address a specific area where you don't want it to have the authority to pull it down. Like maybe it's an area where, yeah, I know that as it sweeps through this area, it actually pulls down too much, and I don't want that. And you can limit it in that region, and then, but that's what this would be for, right? So here, even though I gave it -3 in that one area, or in the total, in this area, it's only going to get 0.2 or 1.8 here, right? It's not going to hit that 3. But if I have 3.5 here and 2.1 in that other, the limit, there's no point having 3.5 here because they'll never hit this limit, right? So if you go to that gain again, 355 is what I have, so we'll just go -3.55 because that's the limit that it's allowed to use. And then this table says where it's allowed to use that limit. So if we look now at the idle again, we're a lot closer to our curve now. Yeah, she's really riding along pretty well here. Idle's coming down, it's 1460. Here's 1450, 1460. So we're within 10-15 RPM as we're idling down now. Can't complain about that. That's pretty good. Little waver on the needle right there for a split second. Probably passing between cells, if I had to guess. You got this position table. Yeah, we just passed between these cells, and they're pretty big changes between those two. I could smooth that out a little bit, might get a little better transition. Like this one to that area, it's a little steep. And we saw that this is actually too high anyways. We saw in that area it was actually a little too much, so I'll just do that. I'll knock it down a smidge, keep it less aggressive. So right now our air is 5.7. Now this says percent. This actually isn't percent in this case. So don't confuse this in idle control with, oh sorry, yeah, idle position, see that? And this, in this idle control mode, and the same for you, Jeremy, this is not throttle position. This is actually grams per second of air based on your grams per second limit. See this table here says grams per second. Now, if we put this to throttle-based idle speed control, this is TMF, that's throttle mass flow. If we put this into regular percentage-based, then this would actually be throttle percentage, but that's not the case right now. But for this, they don't change that. So this is a little overactive right here. You'll see it's a little overactive. The throttle plate is steady. At least on this screen it is. Let's go to the drive-by-wire screen. Look. Yeah, so the pedal's steady, as you can see. But we're getting a little oscillation. So that means right here in this point in our idle closed loop, our gain's a little aggressive. Just a smidge. And so our derivative is our largest source of that. And we can take it and we can add a smidge of filter to it if we wanted. You see it immediately tone down that reaction. But what you'll also see though is that the error is vibrating really quick. So the error itself is causing the overactive derivative, not the derivative causing the opposite. So by raising this filter, the error takes longer to update, and then that calms everything down. But I don't want it to be too calm, because I want it to be pretty aggressive in controlling it. And it was only in that one spot where it was getting a little too reactive. And what you can do is look at the overall ignition advance at that point and how much throttle it was. And if it's in an area where you've just given the air too much authority, or the timing too much authority, by giving it too much air, then that'll happen. So idle control is kind of interesting because you have to, if the car has big cams, for example, you got to give it extra air and have the air always there and run the timing really low, so that when you need to accelerate the engine, the air and fuel are already there, and you just increase engine torque instantaneously with a little more timing, right? If I add timing, that instantly affects the torque output. I have an engine turning 1,000 RPM, That's multiple combustion events per revolution. And each combustion event relies on that spark advance to give it torque. So I can affect the torque output of the engine many times per second with idle, or with ignition, as long as the air and fuel are there to provide that torque that I need. So if you got a really big cam, you need to give it more air, and which means that you end up getting more fuel in there to run the same correct AFR, which means I have more available power in the engine. But I don't use it because I have less timing than needed. And then when the engine goes to slow down, I just give it timing, engine torque pops up really quick, and it keeps the RPM steady or stable or more stable, keeps it from dying. If I rely on air to do it, especially with a big cam, if I rely on air to do it, I have to have a movement from either the throttle plate, I have to have an increase in duty cycle from the IACV, or I have to wait for a stepper motor to move out some. And then after that mechanical action occurs, which takes time, I then have to wait for the air to accelerate into the engine to raise the engine torque and everything. And then by then, the transient is already deep into, dropping engine speed or raising speed, whatever it may be. And it makes controlling idle more difficult because now you're waiting on something to happen and you get oscillations or just really poor idle control. So when you have an engine that has big cams in it, has a really weak air signal, some people call it an air signal, it means that the velocity of the air is really low because your 6-liter V8 or whatever has such a big cam, it's only ingesting like 1.5 liters at idle or something. You need to put in as much air as you can so you have as much available torque there instantaneously, and then you just add a smidge of timing, engine torque goes up, holds RPM steady. This car has decent sized cams in it, but because it has ABCS, there isn't a lot of overlap, and that helps. It helps it ingest less exhaust in the intake stroke, but what it does cause is that piston to push out a lot of air, and near the end of the intake stroke and into the compression stroke, it pushes some air back out again. So it still helps to increase the amount of air that you feed the engine, and then rely heavily on ignition advance to control speed, because again, that's instantaneous effect on engine speed. Overall, though, this was a beautiful start on the cold engine. Nice warm up, no oscillations, a couple little burbles, and that was it. Extremely steady. It's idling right now. I mean, what's the error on that? 16 RPM. I mean, that's almost at the limit of the sensor's ability to determine what the RPM is. So it's really good. So this is really good. And you see here too, I have the deadband set at 0 RPM for ignition, so it is always adjusting ignition to control idle. And I mean, I can bump that up, and sometimes it's okay to bump it up, and sometimes it creates oscillations when you bump it up, especially if you give it too much. If I gave it 25 RPM like they say is normal on this, then what we'll see is that the green line starts to depart more from the purple line. Now I got a sustained error that's 30, or it's peaking around 30, but it's definitely more error than I had before. So it depends on each car. You really got to kind of feel each car out. But see here now that error has dropped down back into the teens. A couple small blips into the 20s, mostly it's in the teens. So things like that make a big difference. It starts real cold. As it gets warmer, starts bouncing around. Yeah, well, you saw what I did here on this cold start. So if you look at your positions for your idle air, see where it's at, check your filters, check your deadbands, check your integral clamps, and all those things. You can definitely polish that up. And if you wanted to as well, in idle control here, in your closed loop, say in your integral, this is vehicle speed. It doesn't have to be vehicle speed. That's barely needed. That's kind of a shitty one, honestly. It's mostly this vehicle speed one is helpful if you have a car that tries to hunt while you're driving and it goes to idle. You push the clutch in, put it neutral, goes to idle and hunts a bit. Then you may find that you just have too much integral at that point because you have other things bumping the speed. You have your fan, potentially you have your power steering, you have your air conditioner, and you just have a higher rolling speed at idle. Sometimes you can use this and give it, as you see here, less integral as it rolls. but overall, it's not really that needed. So what you can do here is change this to coolant temp, so that if you find that there's a spot where it just becomes too active, maybe it just needs to have less authority at different temperatures, which is absolutely viable too as things warm up or whatever. So you can do that. There's a few things you can do. This one here, like I said, it's not super handy unless you have a car that oscillates a lot. But even then, the best way to handle that is not necessarily to give it more or less authority, is to get your position offset correctly, or have the initial closer, because when you roll, you get a higher target idle. In some cases, some cars are programmed. I usually add 50 to 100 RPM rolling, and then that puts you in a new cell. And if this cell is too much, then it may try and flare, or if it's too little, it may bog down a little bit and doesn't really get you in there. And then when you, the other thing you can adjust is target offsets. Here you got your startup, engine fan, aircon, power steering, and boom, right here you can change your target offset based on, you can change this axis to vehicle speed if you want. And so vehicle speed can add to your target. Sometimes they have it already in there under their main, whoopsie, out of control TMF, startup throttle, where is it? Yeah. Some of them have a hard table already. Or like right here, this one, my main idle target table, I have vehicle speed in it. So this is where I added the speed for the idle target right there. And so if I do this correctly, what happens is my idle target goes to 975. So my target when rolling goes 975, which then puts the valve at around 5, right? So 5 should be enough to keep going at 975. If it's not, then I need to tweak this spot a little bit right here. Or if I find that when the car's not rolling, this is what it needs, but when it's rolling, I need a different amount, then I would go into my position offset, and I would go to a table here, and I would put, instead of AC switch, I'd put vehicle speed 0, vehicle speed 2, vehicle speed 10, and then add a little bit of duty at the higher speeds if I want. So those are things that you can do for that. The dyno cell is I can't read it because the laptop turned back too far. Let me. 45 degrees today, Fahrenheit. 45 Fahrenheit. That's what it is right now. All right, well, we're fully warmed up. That all worked great. Now I'm looking at this turbo speed, see if that's freaking working, because that was kicking my ass yesterday for some reason. Turbo speed. Nope. Not yet. That didn't work. Going down, and that's kind of irritating to me, honestly. Like, I'm not getting the low I'm supposed to get, and I'm not using a pull-up resistor. That's irritating. So like 3 is too high, it needs to be like 4, but the output's supposed to be 5 volts, and it's supposed to be a good 5 volt wave. So having it stick at 5 volts, that's annoying. We got frequency, and as it slows down, frequency goes to 0. And voltage goes to 4.7. It's so annoying. Got it on the correct 5 volt source. I've got it on the correct ground.
super fancy little box.
Yeah,
too.
the purple. Yeah. Yeah, these things are supposed to kick ass.
Yep.
For ethanol cars, I think it's the way to go. Stock are those.
Yep. I put on my little chart of plugs to order, I put high horsepower ones, the ones we put in Skies, and then it said extra high horsepower ones.
For those, yeah, perfect. That's awesome.
That way if we need to reorder, these ones we have to get direct from NGK.
Okay.
But overnight shipping's only $20, so it's really not.
Right.
I ordered them last night.
It's better to keep them than not pay overnight shipping. Right. Yeah.
But we can't get them.
Right.
So,
Cool. Yeah.
If
So
you needed one.
for high horsepower ethanol cars, that's what we want. Are those? Because there's 6.
Okay.
Obviously, for gasoline cars, that would be good because there's a 6. But for an ethanol car, that's great.
Yeah. Well, that car's never going to see pump gas. So.
Right.
Same with like Mike's car, stuff like that.
Right. It'd be great for him.
Cool.
Can't think of a good axis for that. Question is, will it hold? Will it hold at high RPM? Because it was dropping out yesterday at low RPM, or at high RPM. So we'll see if it holds out at high RPM. All right. The turbo does not stop. In case you're wondering, the turbo does not stop. That's just the sensor being done. Turbo speed. What kind of sensor can track that? Speed's that high. Turbo speed sensors. The turbo speed sensors, they have a circuit inside of them that cuts the frequency down by 8. They have a divisor circuit in there by 8, so they output an eighth of what they're actually seeing. So you have to know that when you're doing your stuff. So yeah, it was on 8 earlier, and it was dropping out. Hold on a second. Someone's at my house. Oh, it's UPS. Bunch of boxes. Yeah, so it was on 8 already, and when it got above like 65,000 RPM, it just stopped. It just sat at 8 volts. Honestly, it's almost behaving like it's not close enough to the compressor wheel. The way it's being, it's almost like it's not close enough. And I can imagine that something that goes that fast and has that little mass to it, because the fins are really thin, but they're non-ferrous, right? Magnets aren't going to stick to them. So you're relying on a non-ferrous material to pass in front of this sensor that's supposed to somehow sense the change in magnetic field from a non-ferrous material. So it's got to be pretty sensitive to do that job. So yeah, it's tough. UPS guy is still sitting in my house. Nobody's trying to call me. Look at the phone. Fussing my car. UPS guy is my number. I know that's funny, but when you live in the sticks like I do, it's handy. It's a brand new sensor, so I don't think it's bad. I mean, it's literally brand new, so I wouldn't think that there's anything wrong with the sensor. How does it affect tuning? Well, it tells you some things. If tells you some things, like let's say you're tuning the car and you're looking at the power curve, you're like, man, it's kind of weak, you know, it's not really good, it's not that good. check turbo speed and see what's going on. Maybe you got a leak you don't realize. You know, oh wow, the turbo speed's really, really high. My wastegate duty cycle is really, really high, or whatever. You can look and see, you know, what could be causing it. This car doesn't have EMAP, so turbo speed's really handy or helpful in that. Also, I can look at the compressor map, and the compressor map, one of the sets of lines on the compressor map for the turbo is turbo speed. So when I'm tuning the car and I'm watching where I'm going on the map, I look at the boost, I look at the turbo speed, I can go, oh, well, I'm right here on the map, so I'm pushing exactly this much air out of the turbo. And if my horsepower doesn't coincide with that, I know there's a problem. If I tune a car and it runs, you know, continuously 110 on the dyno on a medium temperature day, I anticipate that it's going to go a little faster speeds on a hotter day, slower speeds on a colder day to get the same boost. If I start getting faster speeds on a colder day and the boost hasn't gone up, then I know I probably developed a leak or something's wearing out or something like that. So it's really good for telling you exactly where you're on the compressor map, how much horsepower you should be making, how efficient the turbo is. If you look at, at 27 pounds of boost and 127,000 RPM, you know where that is on the compressor map. I can look at that and go, oh wow, I'm only at 61% efficiency on the compressor there. If I lower the boost down, it might pop me into a more efficient island, or maybe up even, based on the shape of the map. You may find that you can increase the efficiency by pushing it just a smidge harder, which is counterintuitive, but that's why having the sensor, the speed sensor, is so handy. You can identify intake restrictions with turbo speed. You can say, oh, you know what? I know where it behaves on this map. If I had a turbo that was more efficient right there in that island, then that would give me information too. So you can go, oh, you know what? I need to just go up one step in turbo, and I'll gain a ton of efficiency where this thing is running. Or you can look at your map and see where it runs on the compressor map during a pull and find out you're never in any efficient zone on the compressor at all. The entire pull, it goes to the top of one zone, goes way over the main efficiency island, and goes across out to the backside, and you just never operate this thing efficient at all, and you have completely chosen the wrong turbo. You can change turbine housings, and that affects back pressure, which affects flow, which also affects turbine speed, which affects a lot of other stuff too. So you're, man, it is really inefficient right here. I need to do something about it. Well, what symptom am I seeing? Well, speed's too high, or my boost is too high. Well, I'm just change turbine housing, and then speed should drop me down to a more efficient zone. Less back pressure means less boost for the same horsepower. Drops me into a more efficient zone. Or the other than that, you have a car that's a little too laggy, and you look and you're underneath the efficiency island through most of the pull, and realize that you would gain power in the mid-range and probably even at red line by going to a smaller turbine housing. Not often you gain power at red line in a smaller housing, but if it's just too freaking laggy in the first place, you can increase area under the curve dramatically with a smaller housing and put yourself straight across the middle of that efficiency island on the compressor map. So there's a lot of things you can do that you would never know where you were without the turbo speed sensor. Yeah, it's very different, Jeremy. The higher you are, the higher the speeds are going to be to hit the same boost levels. And this is not the first car I've had turbo speed on, so it's significant too. Even from here to sea level, which is about 2,000 feet, I think Anton was seeing like 15,000 RPM reduction going to sea level. It might have been more than that, but it's a lot of RPM difference. Okay, turbo speed is not. Actually, I'm back to second gear. See the gear detection? It said I didn't know what gear I was in, so let me go back to that second gear. Didn't have problems, or was that when I pushed the clutch in? Right there. Gear ratio 71.6. bump the tolerance up. But you can see here, typical speed, typical is 8, I got it doubled, so. Alright, so that's good. Like that. Alright, let's see if boost works. On the gate. Why is that? Huh. It's at 25 psi on the gate. That's annoying. 0% duty cycle on the booster solenoid, 25 psi. Oh wait, that's not where I'm at. Right here. 5 on the solenoid. So 5% duty cycle. I'm getting 25 psi. It's almost like it's creeping. Like I'm looking at this, the way it's slowly rising, it's like boost creep. You can see where I left off the throttle blade. Look at that. So that's something actually I think is good to show you guys. A lot of people think that the EFR recirculating valve internally is adequate. It's not. And that right there shows you why. It is not adequate. Here we go. You see it's not adequate by the pressure wave. Look how long it carries. Up, down, up, down, 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 like that. Look at that. Zoom in on it. Now, that spiked up to over 30 pounds right there. Now, that's on the boost pipe side of the butterfly. And that was not adequate to do it. Now, does this have a blow-off valve on it too? I don't know if it's got both. No, it doesn't. It doesn't. That's why it's so bad. I've blown intakes up, and that wasn't even full tilt, right? Like, that wasn't even full tilt. I've blown intakes right off of intercoolers with this fucking turbo speed. God damn it. It is not working. It's actually the exact same RPM as before. Well, let's double check that I got it in the right input. I'm pretty sure I do, because you go here, check our inputs, and it'll tell you what each one can be used for. No, not that one. So I have it in, I think I have it in DI8. is supposed to be a speed input. So we'll go search, speed. Give it a half hour to search because it sucks. Talk about which ones to use for speed sensors. I thought it was right there. Pretty sure it's 1 through 8 is the one that does frequency. I mean, you can look at the software when oh, you can't see this part. Anyways, when I bring up the runtime value menu, in it you have frequency detection for the digital inputs. So digital inputs 1 through 8 have frequency detection. And it works until it gets above a certain frequency and it's crashing out. And it's not supposed to, it's supposed to be fine. So I'm technically on the right input as it says on the instructions. I've got the 0 volt sensor ground. I've got the 5 volt sensor output going to it. And it's the only thing on that 5 volt output. So with the only thing on that 5 volt output, I don't see why there's any issues with it. It's annoying. Let's see. Digital inputs 1 through 8 read frequency range inputs to 25,000 hertz. I'm not anywhere near that. Turbo speed 1 and 2. Sure enough, there you go. I'm not anywhere near 25,000 hertz. And I'm like a tenth of that. And it's still crashing on me. But the voltage is just failing to high at the high RPM for some reason. So it might not be close enough. It could be a shit sensor. It could be just not close enough to the turbo. And it's losing signal, can't produce a signal, but the wires are good, they're going the right place and everything else. So I suppose it's also possible the wires could be too close to something else and they're picking up noise. I don't think that would just lock it at 4.7 volts like it's doing. If we look here and we go just after it quits right here, then I'll punch in DI7 voltage 4.945, and it just stays really high in the 5s or 4s. 4.7, 4.8, 4.1. This is it's not giving me a significant low. Like it's supposed to pull down and give me a very low voltage in this. It's supposed to be a square waveform. goes, let's see, 0, 1, 2, 3, 4, 5. Yeah, it should be 0 to 5 volt waveform. I'm not getting it. Huh. 8 count divisor, 5 volt supply. It says here 5 to 9 volts. Probably not deep enough. I suppose it could be too close too. If it's too close, that could cause it as well. But, oh well. Man, I really wish that worked. I really wish boost would work correctly too. 25 pounds. That makes boost control easy if I don't have to do anything. But that's not what I want. Shit balls. I got 14 pounds of boost by 42. Oh, well, fixing the leak increased the boost for sure. Look at that. Yeah, fixing the boost leak made a big difference. I've got so dyno holds it steady, boost builds while the dyno holds it. Without the dyno being held steady, whoops, it's only a couple pounds of boost by 4,000. So, that being said, though, that's not the same because it rolls without load to that point. Whereas if you were in a car, it would have load to that point. So the boost is more likely going to be around this point by 4,000, which is, around 8 pounds. Oh, more than that. Yeah. It's like 12 pounds. So that's good. That's a lot less laggy than it was before. So the boost leak or the split line, fixing that has helped a bunch with that, but it hasn't got the boost come down any. Weird. Oh, look at this, turbo speed comes back. Yeah, so right at that same frequency, right around that 64,000, it cuts out and comes back. So yeah, it's either too close or too far, unfortunately. Alright, well, I guess we'll just fix the fuel and add some timing up top and see what it makes on 25 pounds of pump gas. It's just going to have to be the deal, I guess. Tuning, fuel, main VE. This is where we're at. And let's back to the logging. Right here. Tune. So I'm rich as balls. I'm 7.3. It's pulling 2% fuel out. It's not pulling a lot of fuel out, so it's not acting extremely quickly up top. So if I want it to do better up top and pull more fuel faster, then that will involve changing the PID control for the system. The way this system works is pretty interesting because I have here's the transport okay, that was weird. Transport delay here. It's how much time I think it's going to take to get to the sensor. This is a little low, actually, especially for that. That's a little low. probably bump that up a smidge. We'll actually make it. This is just like how long do you wait. This tells it where that measurement is in relation to the engine cycles. These are zones for the long-term trim, which we don't really care about right now. This is the limits. It's allowed to pull 10%, is where it's at right now. It's allowed to add 25, right? We did that earlier. So if it runs lean for anything, it can do that. But then we get closed loop setup. We go to the PID, we check the dead band. It's 0.005 lambda, which is a pretty small dead band. Then we can look, as we get closer, as we get higher in RPM, and closer to target, it has less authority. So if it goes way outside the range of lambda, it's got a lot more authority, but down at the 0.02, it doesn't have a whole lot of authority. So that's why it's not being very active to arrest the RPM. Now, this is proportional, right? So proportional is only going to get it so close. That doesn't build up. Integral builds up. And in this one, if you look here at the higher boost levels, I have integral turned way down. And that's good for initially, because we want to make sure that it's not going to go crazy on us and pull or add too much too fast or create any oscillations. I think we see that it doesn't. And then derivative here, hardly any derivative, and that's good because derivative with air fuel can be kind of funky because there is a time delay with the air fuel, with the transport delay and all that. You can induce oscillations pretty easily, so you don't need a lot of derivative on that. But I gave it a little more authority to pull some fuel. Now, that being said, I should make it so it doesn't have to pull so much fuel. So we'll go to the main VE table, and we'll look at where we were. Where did it go? It is not. Here's our spot. That's where I want it. Tuning, fuel, VE1. Oh, we're off the table. Well, that's why then, because we're off the table. So this table was originally set up for pressure ratio. That's why it only goes to 200. This was set up before to be the difference of pressure across the engine. So 200 would never happen. It'd be 200%. That would never happen. But now that since this one does not have EMAP, I need to extend it some more. But you see how high this VE is? This VE is unrealistic. The VE up here in this load we're at now is probably going to be less than 100, probably closer to 95 or so. When you get that high a boost, your exhaust pressure goes up, and it's a lot higher than your boost pressure, so your volumetric efficiency actually drops. A lot of people don't realize that. Your VE drops after your tow point, where the exhaust pressure goes higher than your boost pressure, which on this car is probably around 4,600 to 5,000 RPM. It's going to actually drop even more. And here you see it actually set up to be even richer, and that's something I do in these areas just in case something's funky. But also because this was, like I said before, for pressure ratio instead of for just manifold pressure, then that's why that is different. In the real world, if this was based on difference of pressure, I would have been down here on the map at this 90 mark at 90%, because like I said, it'd be around 90% efficient, because I would have higher exhaust pressure than I had boost pressure, so I'd be down here on the map, or even down here, somewhere in this range. But because this is now manifold pressure, we're actually operating up here. As far as where we are on the table, the value is not great. The value is really high, which is why it's so rich, which again is for safety reasons, while we figure out and work out all the little kinks with this. EMAP would definitely make it a little easier. I really like tuning the EMAP. The cool thing about EMAP tuning, or pressure ratio tuning with EMAP, is that the fuel map doesn't have to be very big. You only need to go from 0 to like 150%. And here you see the 200 is way more than needed, because we would almost never, ever get there. And so your fuel map shrinks down in size, and you have a lot less tuning to do if you're tuning this zone instead of tuning this many zones, right? Like, it's just a whole different size with the pressure ratio tuning. What you don't realize is that the pressure ratio on the engine, if you were on the highway, at like, you know, if you're cruising on the highway but you're doing like 80, for example, so you're doing 80 on the highway and your RPM in the Super is like 3,500 RPM, that pressure ratio would be the same as if you were at 20-something pounds of boost at that RPM. So essentially, when you tune that pressure ratio zone, you also tune a really high boost area. So as long as you cover pressure ratios up to like 120%, you don't ever even have to hit those high boost areas to have that fuel table tuned, which is really cool. So like, I can tune a car for 60 psi and never break 14 psi because I will have hit those pressure ratio zones already. And then the only thing that increases the horsepower is the fact that the air is more dense. And so people have a hard time understanding air density compared to volumetric efficiency. People think that if it's moving more air, you have a turbo on it, well then your VE obviously went up. Well, that's not the case at all. The VE only goes up for, like I said, a very short period of time, and then the VE drops with boost. But the air density goes up a lot. And so when you hear, who are you guys online that say air density all the time? The diesel guy. What's the diesel guy's name? Banks. There we go. Fuck, Banks. So, he always talks about air density in the manifold. We got to raise that air density to make power. That's what we're doing here with this, right? We're increasing the air density to make power. And, oh, here I said Banks. There's a little bit of a stream delay, apparently. And, that's what we're doing, right? But to do that, we use exhaust pressure and energy from the piston squeezing the exhaust and pushing it out of the engine through the turbocharger. So the horsepower to turn your turbo is not free. Some people think it's free horsepower. It is not free. It comes directly from the crankshaft via the piston, compressing the air between the turbo and the engine. That's the horsepower to turn the turbocharger. And so if you think about how much higher that pressure becomes at the higher loads, you understand why the VE drops, because you retain more exhaust gas and there's no more overlap flow and any of that kind of stuff. You retain more exhaust in the engine. So VE drops, but we've increased air density enough that we are able to make more power. And that's also why with some turbos, there's diminishing returns. There's a point at which you push the turbo so hard, you stop making more power because you're retaining tons of exhaust gas and you're losing tons of horsepower on the exhaust stroke, compressing it to try and spin that turbo. So that's why there's diminishing returns, and I hope that helps for those of you that get confused. It's hard to understand sometimes that the VE drops as boost goes up and power goes up still. So that's a hard thing to wrap your head around sometimes. That being said, Gale Banks. I can't remember his fucking first name. I knew it was a androgynous name. I say androgynous only because he's the only guy I know named Gale, but oh shit, so it's my house again. My wife. Okay. Whoops. I'm gonna do that. Alright, so what it does is it interpolates the new values. So the ones that are the same stay the same, but then it interpolates based on the last couple cells, and you can see it went crazy up top, which is fine because it's not gonna be that high anyways. So I'm gonna grab the 200 cell here, the 110, which is still high. Actually, I'm gonna go lower. I'm gonna grab the 102 cell here. I'm gonna hold control, and I'm just gonna go up, bloop, like that. Now they're all the same. They're all the same. And where we were before was 112, now we're at 102, so we dropped about 10% fuel out of it. Now, 10% fuel, is that enough? Let's find out. So our target was 7.66. Our lambda was 0.738. So we're looking at 3% fuel error there, but also it already pulled another 3%. So 6% fuel would get us to our target of 766. But 766 is still pretty rich. That's, you know, what is that, 11 11.0, 11.1. Let's double check. I don't have it always memorized. 0.766 times 14.7, 11.2. Okay, so actually that's good. I guess I put it in the right spot initially. So I only need to drop about 6% out of it at that range. Okay, so we go back. So I'm going to raise it up. Again, this is a start. That was weird. Right there. Nope, that right there would be about 6%. Go to our next spot here. Do a little bit of this. Then take this and go back down. Do that. Alright, so that's where we're going to sit right now. I'm going to copy this table. I'm going to go to VE2. I'm going to paste this table into VE2. Now that does the axes and everything for me. I'm going to select all of VE2. I'm going to add 5% to it. And then we're going to VE1. And this will lean it out. This will also advance timing. Now, you may go, wait, what? That's a factory Subaru thing. Well, this is too because I set the timing up based on air mass. So if I reduced the air mass by 6%, then the timing is going to be advanced by that amount, which is only about 1.5 degrees, which is fine. That's totally fine for this next pole. And in theory, that should increase the power. Better fuel and more timing. So let's set the dyno real quick. See what we got. It added about 1 degree of timing, as expected. Air fuel is closer to target. The correction now, it actually is adding some fuel, but by adding some fuel right there, we were actually richer than target. Up here on top, though, in those high zones we were just doing, it was still pulling about 1%. So this is the area that we just did. Right here, we're still pulling a little bit of fuel, so it's close, but pulling some fuel. And then up here, it's adding in this zone, in that spool up region. If we go to the air mass plot, we can see throttle air mass is less than the map air mass through that whole region where it was lean. So those changes I made, remember I changed the throttle air mass before? It was just too much because now this throttle air mass is actually below where it needs to be. So I need to do a small change of that. Once I get the throttle air mass, once I get the map air mass to be correct and give us the right air fuels, then I work on the throttle air mass to get to match that. And I don't even have to make the throttle air mass in control of the engine. I just run it in the background like it is right now until it matches. Then I can just blend it right in, or give it control if I wanted to, based on where we're going. So, all right. Okay. Now, that didn't make any more power. It didn't make a graph either because the data computer's screwed up right now. But, let's see, the number didn't look any bigger. Oh, it made a lot more power. I just stopped the pole early. Made a lot more power in the mid-range. Like 30 horsepower in the mid-range. Up top, it made less because I stopped the pole so early. Alright, I gotta reset this dyno because the software keeps glitching out. Let's go look at the knock control stuff. I don't have that totally set yet because I want to see what the engine noise is going to be. Typically, I do the knock control stuff on ethanol a little bit, but so here's our engine noise. There's why it made hardly any power, because just the background noise is breaking over the threshold a little bit, so it's pulling a bunch of timing. Now I know it's not real because there's no way having 3 degrees on the cylinder is going to make it knock, or having 11 degrees on this cylinder is not going to be knocking. So that is just a factor of this engine noise is going over the threshold. Looks like I got not enough ramp on the threshold. So here's our timing poles. But this is all, like I said, preset conservative so that I can fine tune it when we're on here. So you see that the noise, so the threshold I could drop down here because the noise is low, but as it goes up, I'm actually surprised at how little the noise increases. That motor's actually pretty quiet, considering it goes from, was that 500-ish to, you know, around 12 on the big peaks, but the averages, only this much. Usually the engine noise goes up quite a bit when they're big forged motors and stuff, so I'm actually happy with that. The motor sounds super quiet and super clean during a pull. So it looks like I got to lower the gain some. I got too much gain in the mid-range here. So I'll lower the gain, double check the frequency that I'm in, and then adjust the threshold a smidge until we get a little better result before I start adding too much timing to this thing. Yeah, so the gain's set at 4, which I default on base maps because it's normally set like 2. These sensors in these cars are pretty loud. "11" is early on this engine, or 10 degrees before top dead center is actually early for an EJ, but it's fine. 50 degrees is long for an EJ. But, you know, it's fine. You're not getting a whole lot of valve closures 40 degrees after top dead center. But this 10 degree one is a little problematic. I wish the start window was adjustable based on cam timing, because intake valves can trip it, so you really deal with some BS with that, I'm gonna tell you. Okay, so that looks fine. I'm gonna leave that like it is. Lockouts, 7,500. Knock does not really occur over 7,500 RPM. Knock usually doesn't occur over like 6,500 RPM, which is why I think it's funny a lot of people take the knock tables on like their stock Subaru and they see it stops at 62 or something, and then they'll add a bunch of RPM to it. Well, I'm operating up here. Well, knock doesn't happen up there. Like, the piston speed is so fast, especially on an engine like this that has such a shitty rod ratio. Well, not this one, but a regular EJ25 has such a bad rod ratio. That piston is just flying through TDC. You're not going to get knock. It just ain't going to happen. Knock is a low and mid-range phenomenon more than a high-range phenomenon. Or RPM phenomenon more than a high RPM phenomenon, because everything happens so quick, and you're already trying to get things to light off, that you're just very, very not likely to have a second pressure wave that, even if it starts, it's not going to have time to transverse its way across the cylinder to bounce off anything. So 75 is actually even a little aggressive, a little high on these. Post-start delay, that's not a bad thing to add, a couple seconds post-start delay. So in case you got a noisy, let's say you got a twin disc, and you push that thing that's rattling away and throw off the knock sensor at startup or on a gear shift, it's a good idea to have that turned up so that after it starts, you have 5 seconds, let the clutch out, it doesn't bang away. Yeah, this should be higher than 5. I don't know why it's only 5. I do like 15. Sometimes even higher than that, 20, 25 even for these. Totally fine with that. This is too low. This is too fast. Typically, yeah, I would say Yeah, we'll do the 10. I like the 10 typical. It's more conservative if you have it lower. Or no, actually it's not. It's less conservative having it lower. Yeah, that's too low too. So we're gonna go for that. Okay. There's only one knock sensor on here that we're using, so all 4 cylinders use that one. Here's the threshold table. See at higher RPM and higher loads, it's making a little more noise. This whole thing is probably going to go down now because I changed the gain. So I'm going to bring this all down to start off with. Like that. And we saw that in this mid-range it actually was a lot quieter than that. So we'll add some, pull some here in that range. Okay. Here we can change the gain if we want. Like say it's and this is based on cylinder. Say it's making too much noise or picking up noise in a zone that it shouldn't be picking it up. We can lower the gain, or if we want this one to be more sensitive in that range, we can raise the gain. Say we're doing engine studies and we find that one cylinder gets a lot more air than the other cylinders. That one we want to turn the gain up a little bit. You know, it's a little more sensitive. We want it to be a little closer to knock. We want to listen a little more to that. We can hit that. And this is a flat gain. And oh, this is the threshold. I'm sorry. This one adjusts the threshold if we want to raise the threshold. But there's no reason, in my opinion, unless you need to do the threshold by cylinder. Like one cylinder is noisier, or in this case, like number 4, the knock sensor is closest to cylinder 4. So the knock sensor is going to hear the valves at cylinder 4 more than the cylinders. So you might turn it down. You might raise the threshold for cylinder 4 only. Instead of raising the gain, you can change the threshold, right? Whereas here, I could technically change the gain for that cylinder. Oh, well, it's so close. Let's make it not listen. This would be a global change. This would make it less sensitive across every situation where cylinder 4 is listening. This one here will adjust the threshold just to give a different threshold based on whatever I want. This is based on boost or efficiency calculation, which here is boost over baro. But I could do it based on RPM. I can do it based on whatever I wanted to. But overall, this is pretty basic right there. It's 1 is good. Shouldn't need to do a bunch of crazy compensations unless you got the engine on an engine dyno and you're doing lots of studies on the thing. Otherwise, like this, it's a lot of guessing until you get some noise profiles by doing some polls and get an idea of what it's doing. So. The other thing too is those guys were really, really active, getting a lot of noise on that thing. Like it was a bunch. Where are we at? So here's what I was looking for. This is the frequency and the bandwidth. So we see it's a relatively narrow band centered around 7,000 hertz. And then based on the filter window, you get the shape of it. That's a strict band pass right there. This gives you the fatness of it and the steepness of the slope, how hard you're cutting off those other frequencies. And you can change this frequency and see how it picks up noise. You can also use a calculation to determine where your center frequency should be on this. Subaru, I thought, was another 1,000 hertz up, more of a 11, 12 to 6. This might be a little low on the frequency, but like I said, it's with a calculation, and it changes a little bit based on the engine. It also changes based on things bolted to the engine. big steel header that's cast iron versus a tubular header that's, something else, will affect how well the noise resonates in the engine. Doesn't really change the bass noise because that's based on the bore, but it changes what sounds will propagate to the sensor themselves by changing the resonant frequencies of the block with what you got bolted to it. And if you think about that, that makes total sense. Manufacturers do that on cars all the time. They'll just bolt a weight to something, right? Oh, this thing is buzzing too much or noise is carrying through it. They'll bolt a weight onto a control arm or onto a diff. My BMW's got a lead weight hanging on the back of the rear diff. Just this little lead weight about this big. It just bolts on, whoop. It just has one bolt in it and sits there. And its job is to change the resonant structure of that structure, or the resonant frequency of that structure, the rear end, or the control arm, or whatever. So the same thing happens with an engine. You bolt on a big header, you bolt on a different intake manifold. The mass of that, the density of that is all going to change what kind of resonant frequencies you get out of your engine. And so there will be some slight differences. Ton more noise per mine. Yeah, is yours level 4 though? I don't think yours is level 4. It might be. I can open yours up and look. And I don't even know where yours is centered at. So I'm actually curious about that. Let's do that right now on channel. Let me save this. And then let me disconnect from the ECU. I'm just going to pull my adapter out. Just save myself some time. I'm going to go to Discord and I'm going to pull your map off it because I didn't do it on this laptop. Yours down at 6, and your bandwidth is 1,000. So your bandwidth is different than this car. So you're down here further, so 1,000 less, and bandwidth is 1,000. And then you have what? Engine functions, knock. You're on gain 2, yeah. So that's totally different than yours because we were on gain 4. You've got different retard rates, but that doesn't matter. Oh, and your window's the same. Okay, that's good. I like that. What else you got done on this? 15 to 7. All right. You got some post start in it. Okay. Same there. Your threshold is strictly RPM based, which in theory makes sense, except when you think about the mass that you're putting in the cylinder. The mass you put in the cylinder affects the way a wave propagates, right? Sound travels different speeds through different densities. So the speed of sound changes with the medium that it's in. So technically, if I have more cylinder pressure, the sound is going to travel a different speed than if I have less cylinder mass, less charge. So a knock that happens at 6,000 RPM under vacuum will have a different frequency than a knock that happens at 6,000 RPM in high boost, right? The density of that charge is very different between the two of those, and therefore the speed of sound is different between the two of those. It's not way different, but it's like 20% different, which would affect the frequency. And based on that curve that you see, let's say it pushed the frequency up some to an area where it was less sensitive, then technically you need to maybe lower the sensitivity in that region because it's not going to trip the higher ones. Or if it lowered the frequency, you have to change the sensitivity in that region based on that too. So just there's a lot of weirdness with knock control and a lot of theories and stuff with it too. And a lot of the best books a lot of the books out there mention that even the best written books on engine fundamentals say that often the human ear is better than a computer at detecting knock. I agree with that in the sense of extreme knock. I don't agree with it in the sense of light knock, because everything is so damn loud you can't hear shit. But if you had headphones on, right, then yeah, you can hear it really darn good, which is great English, I know. But if you have headphones on with an amplifier and you're listening to the knock sense on the engine, you are more likely to pick it up than the computer will, because we're trying to make it say, listen to these frequencies, but our ear's going to hear rattle, squish, you know, in there, and it's going to be kind of two different peaks that we're going to hear in the engine. There's the initial combustion that happens, and then there's the aftermath, and so we're going to hear these different frequencies, and we're going to recognize them as being very different than the other sounds around them, whereas the computer can only look at amplitude and frequency a little bit, and that's it, and it has a harder time associating with them. So it's difficult to get an ECU to really control knock really well than if you were to tune it with cans on and that kind of stuff. So that being said, I should probably have cans on, but I don't have cans anymore. They died. And I haven't used them in like 12 years. Okay, so let's see what she does. Oh yeah, I got to reset. Let me, let's make sure that's good. still about 10% low up there. Here it's at the beginning of the pull at wide open throttle, it's dead nuts on. Got that really close, but then as the flow went up, it started falling off some. let's check VE first and see how close we are with the tune anyways. We want to make sure that's good before we even fuck with the throttle mass. The throttle mass will be affected by the VE table a little bit. Okay, so we're pulling 6% fuel out still. We're pulling 6% fuel out, and we're 2, 1, 2, 3, between 2 and 3% there. So we've got a total of about 9% fuel that we got to pull out of it. So we're still rich. Timing went up a little bit, as you can see. 11 to 13 now. It's going up some towards red line like it should, instead of flatlining like it did before. Yes, we need to pull some more out of the VE map. Start right here. Just gonna pull everything above it because it's not going to gain VE at this point. We're at a point where it is losing VE continuously. We got 5 VE jump right there. 6, 7, 8, 9, 10, 10. Yeah. It's a lot more. VE actually drops up top, so pull it out here. This now, the drop up top is doing more up here and less up here, so pulling too much out here wouldn't make much sense because it's not going to drop as much as it's going to drop up here. V is going to fall like this off a cliff up to the upper right corner. It's going to drop at RPM. It's going to drop off the cliff on the upper right. It's still going to drop in the higher boost, but not as much. It's going to be more pronounced as it moves up. Attack this spot. I'm going to raise that up some because we're seeing some lean trends as the boost comes in. So this area is getting more fuel, which makes sense because of the way the cam overlap is. Like that. Okay. So where we're here, we've only pulled like 5% out at the most. So a little more here. This table's not being used right now, but it will be later when I add ethanol. The VE2. I'm just keeping it up to date. Let's go to air mass again. Here, the throttle mass leaves when? I'm seeing a 10%, 11% difference here in the air mass. I had to pull 6% fuel out of the map, so this next one, this map should be closer to the throttle air mass on this next pull. The throttle air mass looks like it's actually pretty close to where it's supposed to be. Based on the difference in mass. Oh, I said 10%, that's at 5%, so yeah, it's going to be almost right on. charge temperature thing. And fuel temp. The fuel's getting hot for sure. Closer, but it actually dropped with the VE a little bit, so I gotta get that. I gotta adjust throttle a smidge more. Pressure's damn good now. Alright, so we got 3% coming out, and we're another 2%. So we're still about 5% rich, which is weird because we just pulled 5% out, or probably 3% out of it. But we're getting there. Here it's adding, right here is still lean in this spot. Need to add fuel through here on the map. Right there. So that makes sense because that's before that crossover point. This whole section's a little fatter, which makes sense. You see the table is really flat right there anyways, so we'd anticipate that there'd be some peaks somewhere, and that's a good place for there to be a peak. That's gonna be too much though up there. Now this area is going to be aided by the TMAF once we enable the once we enable the TMAF, it's going to assist this whole region in getting fuel, I believe. Let's double check that, make sure I'm not lying to you. If we go to air mass, where'd we go? Nope, I'm wrong. They make it even leaner. Look at our cams. I don't want to get too hung up on the V curve when I have cams to screw with still. I haven't even moved the exhaust cams yet. So let's do a little bit on the ABCS on the exhaust side. Let's move this cam a little bit. Alright, so what's the exhaust cam going to do? The exhaust cam is going to increase overlap. That's the first thing to think about when you're going to change the cams. Anytime you advance the intake or retard the exhaust, you're increasing overlap. So changes from 0 are going to increase overlap. Remember that. So anything I do here is going to increase overlap. I don't want to increase overlap where I have a negative DP or pressure ratio across the engine. When the exhaust pressure is higher than the boost pressure, I don't want it to overlap because it's going to push more exhaust in the intake side, to retain more exhaust in the ports, and retain more exhaust in the chamber. So I don't want that. If I had exhaust pressure on this car, then this would be way easier because I would know exactly where that toe point is instead of knowing it's usually around 5K on this turbo, and it changes with altitude. So what I end up doing on those cars is the fuel map goes to pressure ratio based, and the cam target tables go to pressure ratio based, so that I know that when the pressure ratio becomes inverted and I have more exhaust pressure intake, I'm removing overlap. So my overlap I have based on RPM and pressure ratio, and that gets you the ability to fine-tune your overlap in your cams like really damn good. And then also it's really important that your cams and your fuel map, your VE curve, have the same axes. It doesn't have to be the exact same RPMs, it just has to be RPM. It doesn't have to be the exact same pressures, but it has to be pressure, right? Or pressure ratio, or whatever you're using for your axes. It's got to be the same, because a change in cam position will affect your VE. So if your VE table is based on something different than your cams, that means at the same spot in the VE table, your cams can be in different positions, you're going to have problems, all right? So it's important that you have your cams at the same, on the same axis as your VE table. The other option you have is to just have your cams based on RPM. I don't recommend it, but if you did, what you would do then is you would, or based on something else, like just boost, or boost and RPM, but if your fuel table was on some other method, you could blend your fuel tables or trim your fuel tables based on cam position. I don't like doing that, but you could, and you can get away with it. But sometimes what you find is when you have that many overlapping tables and variables, that you could tune the car for a year and still never get it close to being right. If you reduce the amount of stuff that you got to compensate for by putting things on the same axes, things that directly affect each other, you're gonna have a much better time, and it makes more sense. Overlap, I deeply care about my pressure ratio with overlap. I deeply care about RPM with overlap. Those two things alone are the biggest functions for cam timing. Like, there's almost nothing else that matters with cam timing other than engine pressure ratio and RPM. So if you know those things, or you use them as the same axes, you will get a much better tune, and you'll get better, more logical control. So now on the top end, if I know my cam profile and I know I'm retarding the exhaust up top, I may have a situation where when this is at 0, my exhaust valve shuts, and the intake valve also being at 0, it opens over here, and I have 10 degrees to play with, right? What that means then is I can retard the exhaust cam a bit like this and not add overlap. Technically not even add overlap, because there's dead space in the cams if they're a small enough profile. And what I'll do there is, by retarding the cam or the exhaust cam more, bringing it closer to the intake valve opening, I don't increase overlap. But what I do is on the other side, when the exhaust valve opens, I alter my expansion coupling versus blowdown. So when the piston's near at bottom dead center, the exhaust valve opens on its way down. Now it can open 50 degrees before it gets to the bottom. It can open it 20 degrees for the bottom, open it like at bottom, right? If you have enough variable cam, right? But the point is, the sooner I open it, the sooner I start my exhaust blowdown. Now what that means is I have pressure in the cylinder that's higher than pressure in the exhaust. If I start opening earlier, the pressure in that cylinder is higher when the exhaust valve opens than if I waited longer, when the pressure goes down more, right? So the piston moves down, pressure is dropping. So I can use that higher pressure when I crack that valve open to blow the air right out of the cylinder and down the header, and create velocity with this burst of air, which creates a very large pulse too. You get a very strong pulse out of that. But then that pressure isn't used to push the piston down as much, because I'm relieving that pressure. The other method is I delay that valve opening, so the pressure is pushing on the piston longer, means I can make more power out of it. And then when I open the valve, there's less of a sudden burst. There's still a burst because there's always a higher pressure, but it's just less, and I have slightly less, I've created less time for the exhaust to leave the engine, which has an effect of actually raising back pressure a little bit. So I open the exhaust valve earlier, I give it more time to leave prior to the intake event, and I have a harder, more active pulse. By going later, I get more expansion coupling. I can technically create more power as long as the increase in back pressure I suffer doesn't hurt me in the long run, right? So you're always balancing this blowdown versus expansion coupling with your exhaust valve opening. And in a lot of cases, especially with forced induction motors, it don't fucking matter. Like, it doesn't matter. The one of them gives up almost the exact same the other one gains. At the higher horsepower levels, like, you can change the cam 10 degrees and you won't see shit. The only time that it hurts you is if you increase too much overlap and retain a bunch of exhaust gas in the cylinders. So exhaust timing is not crazy important for top end power on a forced induction car. On an NA car, though, it does help. Retarding the cam on an NA car does help, because that exhaust pressure is not 2 or 3 times your boost pressure. It's not 2 or 3 times the charge temperature or charge pressure coming into the engine. It's 10%, or maybe less than. If you have the right resonance, if you got a tuned exhaust, and you have that negative pulse coming up to the valve, when that valve opens and you're at a depression in your pulse wave, it's lower, right? So it can definitely make a difference on NA cars. You hear a lot of guys say, oh, on an NA car I retarded my cam and I picked up power, right? And that's because of that reason. That pressure ratio is so much closer than when we have forced induction, we're 2-3 times on the exhaust side. So what is that going to do for us in here? Well, in turbo cars, overlap is handy in spooling turbos. Overlap is handy for emissions. When you retard the cam, you can change the emissions profile of the engine dramatically by inducing either a Miller or an Atkins cycle, depends on which way you're going with it. Move them all one way, move them all this way. Where your overlap occurs, you can put a lot of overlap in it. You can do it at the end of the exhaust. You can do it at the beginning of the intake. You can separate it really wide so that there's no overlap, and then you just blow everything out, and then the piston comes down and doesn't suck any air, and then draws some air out, but then it pushes a bunch out again because the valve's shut. And there's all kinds of stuff with cam time that you can do. But in dual overhead cam cars, forced induction, the biggest thing you're going to get out of it is slightly faster spool and maybe better fuel economy. With big cams, you can make them drive smoother by getting rid of overlap on the exhaust. But overall, power-wise, you're not going to gain very much with a big cam forced induction car. You're not getting a whole lot of power. If you got teeny cams, you can gain a little bit of power on top because you're not adding that much overlap when you retard, or you're not, vice versa. But with big cams like this one, you end up adding a lot of overlap when you go to get more expansion coupling, which just hurts you because you have higher back pressure, and it just becomes you're exchanging one for the other. That being said, I'm still going to tweak it a smidge and see what we can make happen. Engine development at the IndyCar level. I've heard a designer talking about that using headphones. That's wrong. Yeah. For candidate for some kind of AI knock learning. What was the boost control issue yesterday? Can't wait for my KV8. It's going to be a 207. All right, Travis. The boost control issue still exists. We thought we fixed it because we found a split line. Fixed the split line. Still 25 pounds on the gate. So I don't know what it is yet. I haven't figured that out. Fixing the split line definitely improved the spool, though. It spools quite a bit faster than it did. So I'm happy with that. But yeah, I have not figured out why it's making 25 pounds on the gate yet. A 207. Oh, it's going to be cute. A little 207 with a KV8. A little overkill, but it'll be fun. AI knock learning. I don't know. I mean, an AI is still a computer program, and it's still a computer program that listens to frequencies and amplitudes with a different kind of thought process behind them. I suppose you could feed it sounds and say, this is what knock sounds like, and then do that, and then feed it, this is what a valve shut-in sounds like. And it could probably more deeply analyze where the shapes of those amplitudes and frequencies are with the difference and determine them. So that probably is possible, yeah. Because then you'd be able to, right now, for example, right, our knock sensor is biased or weighted at the 7,000 hertz range, or yours is at 6,000 hertz, and it's giving less priority to the other one below it. So technically, with an AI structure, we don't have a filter for it for a bandpass. It can individually apply a weighting factor to each of the middle frequencies, and it probably would not look like a bell curve. It would have a peak over here and peak over here with different peaks, and that would give them the ability to better determine what a knock event would be. Yeah. Oh, we don't know how to analyze the wave. Oh, sure. Unless we told it how to analyze the wave. But yeah. Okay, so right now I don't want to add overlap right now because adding overlaps can make it idle like shit. Don't want that. A little bit of overlap in cruise is fine, but I don't want to do a bunch right here when I'm accelerating off a stop sign because it's already got enough overlap with 40 degrees advance on the intake cam. And that is to increase compression. That if I add more, I'm just going to increase exhaust retention, and I don't want that either. I do want it when I am here in higher pressure ratios, while it's still positive. So a little bit in this region here-ish could potentially increase some spool, improve the spool. So we just go a straight 10 degrees really fast like that. I'm going to blend this down just, over a couple cells, just so it's not a sudden 10. And then blend it to 6 like that with a little bit. And then I'm going to increase this axis. I don't want to get one taller. I told it yes, but it went the wrong direction. Interesting. Okay, so at the high boost, it's not going to want the overlap because it's going to create too much badnesses. Alright, so I've added some overlap there. We'll see how that affects spool, if it does any. It's only 10 degrees, it's not a lot. I can do 10, then do 20 and see what happens, but I got 40 on the intake cam right now in that spot. This is my version 2 cam set, so it's got even more retard in the cam, so that you have more authority to add a bunch of overlap than you would before. So I added another 8 degrees of retard. So the center line of the cam, intake cam, is 8 degrees more retarded than the version 2. Yeah. Now if we do it at light throttles when we're cruising, we can add a little overlap to improve fuel economy, but we kill torque and all that stuff too. And I don't think that that's necessarily what this guy is going for in a race car, so in a region that he's never going to be. Oh, the pit lane limiter. I get great fuel economy on the pit lane limiter. Target. I got no offset in it. Let's go to closed loop control. See what we got. 10%. All right. Proportional is a little weak. Integral is definitely weak. Derivative is probably a little aggressive. Minimum table is a little low. Max table should be enough. So go to the integral and let's bump this up. That does not look like enough integral at all. We'll do that. Let's see if she builds a little faster. Let's see if we can get those targets better. That was a little better. Overshot the targets a little bit. Add some proportional to it. Pull a little bit of the integral out. Let me get closer. Pull some of that out. And save that. That's the wrong button. Save that. Okay, we'll go to logging. Do this, we'll log it, see how well we hit our targets. Well, I can look at that and go, whoops, made that too active. Bottom curve there, you see the cam was going back and forth pretty aggressively. The solenoid was oscillating a little too much. Now, this alone tells me some of it, right? But what I want to know is what was the PID control telling me during this time? Like, where am I getting my overactive cams from? It's one thing to just look at it and say, oh, it's, you know, it's off. The PID is too sensitive. But where's it coming from? So over here on the right, I've got my exhaust proportional, integral, and derivative right here. I can see my integral is 7, proportional is 1.5, and derivative is 0.7. Now that might be right. So let's go the other direction and see what happens. Proportional activated a little more aggressively, but the integral, oh, it's intake. No, it's exhaust. Yeah, integral. Oh, left hand and right hand are oscillating pretty bad off each other. Okay. But we can see here that the integral is a little fast, so I added too much integral on that. The derivative is not super active. 1%, 2%, 2%. So the derivative is okay. It might even be a little too soft in this case. And it's relying on integral. Also, if I overfilter, then the derivative won't respond, and only the integral and proportional will. So double check the filter is a good thing to go back to. Let's pull some integral out of it, but then we'll double check the filter and make sure it's not too high, preventing derivative from doing its job. I gotta pee. Target filter is fine. I'm fine with a 10 target filter. I'm gonna just kill at 6. Derivative is right here. It's a 5. That's a pretty decent sized number for derivative. Proportional's pretty low. Integral doesn't seem that high. So let's go to my inputs. Go to my channel input, go to VVT, see what I got for a filter on this. I got a 10. I got a big filter on it. Let's go to 5. And that will make the derivative do a little more work. And that may or may not help. I may not have pulled enough off of these tables here, but we'll find out. Still wiggling for sure. P, we'll pause that. And it's over here on the right. So yeah, integral is really high, derivative is, oh wait. Integral is high, derivative is really low. So I can ask more of the integral, or less of the integral and more of the derivative. Yeah. got too much integral and not enough derivative. But also, I should look at the percentage of the solenoid, 40%, 30%. So it's in this range. So what I could do is I could see about how much it takes to hit my target and start there. So this feed forward value, it gives you, so the thing I like with the feed forward is that as soon as the system becomes active, it hits you with it. And that can be irritating because you might not need that much. And that's where this max DC table comes in. You can take this, and this says temperature right now, which sure, that's one thing, but I could add RPM to it. And what this will help prevent is it all of a sudden throwing in a bunch of duty at it as soon as the system becomes active, which can create issues, right? If you're at idle or 1,000 RPM and it's not active, you don't want all of a sudden popping up to 40. But in this case here, at 2,000, 25 might not be enough with a linear curve. So bump this up, 45. Start with something like that. Engine temp. The oil's thick. It might need more, might need less. I've never paid much attention. I know it's less on most cars. It's less, but also I don't need cam timing to occur on a cold motor when it's warming up because it just sits there and warms up. So I can do something like this: increase the feed forward, but then reduce the peak so that it can't all of a sudden just go bam and hit you with a bunch of cam advance. Same goes for this minimum table. Yeah, the forward is the forward is a feed forward, but let's go back to the max table here. Let's copy this table. Go to the min table. Now I know it's set at like 30 or 40, so paste this table, and then I'm going to drop these down. I'll just say 30. Okay. Now with the min table, I may decide that, hey, like in this spot, the feed forward isn't enough, right? It's the feed forward set at 40, but that's not enough to get the cams working. And I hit that zone, and then the system adds duty, and then all of a sudden the cams start to move. That's kind of how these things work with these cars. They lag a little bit, and then they finally start to go. You hit like a toe point where all of a sudden you get this reaction. So you want to start where the reaction starts and move from there. And that 40 feed forward might be too much in one spot, but it's not enough in another. So you would raise the minimum higher than that 40 so that you can get that response that you need and have it be quicker, basically. So something like this, for example. Now I don't have anything. Now what I could also do is, I don't do this on the exhaust, but on the intake, my cams have oiling holes on them. And they get their oil from the AVCS. So if I add base duty to the intake cam, I increase the oil in the head. So I would go to the exhaust one. I don't know if I did this car or not yet. Min. Yeah, so at idle, the minimum is 20%, right? Based on this. So it's always a minimum of 20. So it's always going to have 20% idle, so it's always going to have oil flowing through it and lubricating the cams. Max 55. This derivative is 3s. Integral is really low. And proportional is pretty high in 2s. Now, one thing that's funny is, we want to make them similar, but they don't always behave similar. So having the same tables between the intake and exhaust doesn't always work. I want more integral because I was getting hardly any integral action in that log, so pounds of torque down low. That definitely helps. Huh. Should have hit the log button on that. I only pulled to 6, but wow. Okay. Oh, look right there. Intake had a little jitter to it. See a little jitter right here? So it might be a smidge overacted right there. It's a little bit of jitter. That's better than it was. So we're getting closer for sure. Oil temp, actually. I know the thing that shows engine temp as being an axis. Oil temp would be a better axis if you have oil temperature. This car doesn't, but if you have oil temperature, change that to oil temp instead of engine temperature would be a better axis, because that gives you a better indication of what the viscosity is of the oil that's being used in the system. So we've got a little wavy here. Oh, that's a solenoid. Okay, position under target. Okay, the target goes back to 0, and this stays in. And the solenoid duty is stuck at 30. So that tells me that the minimum is too high in that region. Select the tuning. Go here. Cam control. Oh, I smell some oil. I have a little leak or something. Minimum DC, yeah, so we're in that 30, so that 30 is too high. So I need to drop that down to 20, keep it so it can zero itself out. Okay. Back to the log. So here's the solenoid, here's the cam. Look at this, the solenoid is pretty flat, it's a few percent up and down through this region right here, like 37.6, 37.5, but the cam changes a lot. I mean, here's 37%, here's 37%, right? We're talking point something percent difference in the duty cycle of it, and we're seeing movement in the cams. Ain't a whole lot we can do about that, right? I mean, there's not a whole lot we can do to improve that, because that is such a small change that shows that the system is trying to work and do what it can do. That could be old solenoids, it could be the fact that it's big cams on springs and an AVCS on the exhaust. AVCS on the exhaust is problematic sometimes because it can, the engine is trying to retard the cams, and so when you try and retard them with oil, you need them to, and want them to advance again. That's hard to do because the only thing that's advancing the cam is the spring and the gear. On the intake side, it's the exact opposite of that. Everything's trying to retard the intake cam, and you're trying to advance it with oil pressure. So as soon as you release oil pressure, the cam naturally goes back towards retard, no problem. All the friction is trying to put that cam back in its normal position, which is 0, and the oil pressure is trying to advance it to add more. So the exhaust side, now I don't want to be totally misleading there, the oil pressure does affect a little bit on the pushback, but not a lot. Now on the exhaust side, though, it's mostly just the spring trying to return that cam back to 0. And when you add heavier valve springs with bigger lobes, the amount of power it takes and force it takes to return that cam to 0 is much greater. And as far as I know, nobody makes a stronger exhaust AVCS spring. Something I wanted to do a long time ago, and I totally abandoned the project. But because putting springs in those things is a pain in the ass, I couldn't imagine trying to sell someone a spring and say, yeah, just throw it in, because they are not something you just throw in. You need to make a special tool to put the springs in. Once one of those things pops on one, I go try and clean it, and the spring pops out. Ugh, that's just the worst. They're bad. So if I did that, I'd have to create a special tool that would do it. Now that being said, if I leave the cam parked at 0, it's a lot easier for it to stay at 0 because the spring only has to just deal with just the engine friction to keep it there. But if I start moving it and then ask the spring to return it back, once it just becomes kind of chaotic. And as you can see here, here's 37, there's 37.5 or 35.6, 38, 37.1, 30. I mean, like, it's a very small amount of duty. Here's 41, but you see there's a delay in the response of the cam as it comes down. So it's it doesn't take much duty cycle to make that cam move, and then you got to wait for it to come back when you want. And the system's like, oh, come on back, trying to get it to do its thing. So it's harder with big cams to make the system work right. It is too aggressive right here. You can see this right here. I still have to turn that down. It looks like that is potentially the derivative. That might be too active right there. The integral is pretty active too. So integral and derivative are both pretty active right there. Yeah, they're both pretty active. So I'm going to bring the integral down first and pull a tiny bit off the derivative in that spot. Shit. Pull off the integral. Just pull off the integral, all of it. Like that. That's a decent chunk right there, honestly. And I'll pull a tiny bit out of the exhaust derivative. The other one's integral, I mean. There we go. That could help. The other thing to double check is what my deadband is set at. 1 degree. If I go with a little smaller deadband, that aids the derivative in being responsive. But it makes the integral more reactive too, because then it tries to move things around more. Also, this positive clamp, it's only allowed to add 10%. Right now, that's working out. It's actually it could be too much. So we can lower that down. Typically, it's a larger value, but typically it takes more to make it react. So. Alright, I think we're about out of gas. And I smell a smidge of oil, so there might be a little leak I gotta contend with. But on that pole there, with still no timing on it, 12 degrees at 5800 and 15 degrees at 7300. So no freaking timing on it. And the air fuel's 11.0 or so. It made 440 wheel. Yeah, power's dropped pretty hard because there's not enough timing going in. Also, I need to double check the fuel balance real quick before I forget, because this has got stage injection, and so I need to see how much each injector is spraying. So let's do this. Alright, so injector secondary is 10 milliseconds and primary is 4.6 or 5.5 actual. So I need to adjust that balance. I need to get more on the primary. So we'll go to fuel. Oops, come on. Oh my god, stop it. Oh, Jesus Christ. There it is. I'm like, channel, secondary, here you go. So what do I have? On at 10. On at 15, off around 10, okay. Pressure set, manifold pressure, and injection. That's all the same, alright. Go. Oh, there they are. So I'm like, where the hell is stage table at? Balance. It's weird. Got more going on the secondary set of injectors. I don't really want that like them to split it. I like them to split it. So but that's still like that was double the pulse width of one to the other. That's not 50%. That's the primary doing 50% of the secondary, but that doesn't make sense. And let's double check the configuration again. Make sure you got both sets of injectors set right. 1050, 300. Yeah, that's correct. Pressure on. That's all good. And then I go secondary. 1050, 300. Pressure on. Okay. This should be the same as the other one. 1125. 1125, yeah. It's a different angle, but it's the same table. Okay, linearization. 7062. So that's, yeah, that's the same. That's all good. Okay. Just set the same. It's got to be a logging error. It's got to be 4.5 for primary, and then I take a subtractive to get what the secondary is doing. That'd make more sense. It just doesn't make sense for it to be throwing 10 milliseconds at the secondary injector. It just doesn't compute. Oh, interesting. The voltages on the injectors changes, the time changes as they trigger individually based on when it's sensing it. That's exactly double that, right? 6, 12, 8, pretty frick close. It's almost exactly double that. Same dead time between the two of them. Injector timing secondary 450, these are 345. Maybe that's why. I don't remember changing that. Injection timing tables, here we go. Are these not the same table? Oh, they're not the same table. Let's make it the same table. Let's see if that has an effect. Probably got one more pole before I add a fuel. What's fuel temp? What is fuel temp? Let's look for that real quick. Oh, losing connection. Okay. Reboot. slow to start warm. Probably gotta throw some more fuel at it. Either more fuel or more throttle. That was a little long of a crank. Get a big change for that and see how it does. Still crank for a while. I'm going to dry the engine out. I'm going to rev it up and then hold the throttle open and turn it off. Like that. I'll dry out the ports a little bit. That might have been worse. Lower that back down. That might be enough. Usually I'm around 70% right there. Right there. Try more cranking timing, but cranking timing is rough if you have ethanol. If you have a lot of ethanol, a lot of cranking timing makes it harder. And that wasn't very impressive. right, y'all. I'm gonna call it quits until I get some fuel put in. I can put some fuel in it and see if I can figure out what the little puff of smoke is on the right side after we pull. Looks like a small oil leak probably. As RPMs go up, I see it dropping a little on the faster side there. So get that looked at and put some more fuel in it. If anybody has any questions for you, this is weird because typically through these streams I answer a lot of questions, but nobody has asked me any questions. Is there anything I can answer for you while I'm here? Hot in here. I'll tell you about that. Definitely want to work on this cranking or the starting. This is way too much timing. I just want to see what a big change would do on it. Typically you run like negative to 0. Some cars run like 10, but typically you run very low timing in cranking. I should probably check and see if it's even using the cranking table when it's cranking. Let's check that, because that sometimes something can happen. You exceed a cranking threshold and you leave the cranking table right away. So let's see. That was weird. Well, I like that it started fast, but I didn't see if it was actually doing cranking timing or not. Let's do a log. Crank. So here's 0. Here's the crank. 16 degrees. That's a lot of timing. It should be in crank right there. It says it's using cranking comp fuel. It says it's 17 degrees. DI5, alright, so let's go to the log. Let's look at DI5. 0 volts, 11 volts, okay? The threshold is 1.9, so that would tell me it's definitely start switch is definitely on. Here it's off. So it sees the start switch come on. It's cranking at basically a 200 RPM, and then it fires. But it's cranking at 16 degrees. Fox P2, how's your year going this far? I hope 2023 is a decent year for all, but somehow I doubt it will be for many. Yeah, man. I don't have a lot of complaints about mine individually. I don't like the weather that I've had, but I don't like that I didn't get to see my daughter, but that was technically 22, so I guess I'm good there. Her birthday was a couple days ago. She turned 20. Wish I could have seen her, but she's in Kentucky. Other than that, though, I mean, I'm not selling nearly as much stuff as I have in previous years, and that definitely hurts the income some. I'd like to see the income pop back up so I can do more projects and more parts and stuff, you know, and be more involved in the community. But I mean, I'm married to the love of my life, and we have a great relationship, and want when I'm with her, I'm as happy as anybody could ever be. And when she's away, I'm as sad. No, just kidding. I miss her when she's gone, but I get to play with cars and do stuff with my friends. Wish my internet was better at home, so that I shoot the shit out of my friends on Discord because a lot of my friends are far away. I only got a couple friends locally, but when you're in the military for 12 years and you move around as much as I do, it's just kind of the way it happens, And so I don't have a lot of local friends, just a handful, and they all have their own lives too, so I don't get to see them very much. I actually talk more to my friends that live far away than I do to my friends that live local. I talk with them almost every night or every day. We play some games, shoot the shit, share some things, we'll watch videos together or whatever, So, yeah, we're not there in person, but we get to hang out with them, and that's nice. Because I got people in lots of states, and it's cool too because I get to bring people together that way as well. I talk to my friend in Ohio almost every day. I talk to my friend on the coast of Washington pretty much every day. Like 6 friends over there from when I was living over there. Handful of friends that I've met through people in the military in California and Oregon and Texas and Florida and things like that. So thanks to the internet Discord, I get to speak with them pretty much every day, and that's nice. Friends in Pennsylvania, military buddies in PA, in Ohio, and I said Ohio already, Tennessee, and all that. So I'm thankful for that. Wish my internet was better so I could talk to them better and have better quality, but overall, there's a turkey wishbone on the counter, and the wife wants to do the pull it apart and make a wish thing, and I've been putting it off because I can't think of anything. Like I can think of things that I want. I could think of things that I would like to see, but if I had just one wish, I don't know what it would be. And I think that the problem is I'm treating it like it's my only wish that I could ever wish, and I can't think of one thing because there's so many things that I would like to see happen for society and for our country and for our industry and for my friends and for my family. I can't pick anything, and I get completely locked up. And she's like looking at me like, seriously? And I'm like, yeah, man, I can't pick anything. I can't pick one thing to wish for because I want so much for so many people, and I just don't know what that would be. Obviously, it ain't fucking coming true, right? It's just a wishbone, but I don't know. I get hung up on it because I want so much for so many people, and I can't pick something, I just can't pick something. There's so much crap going on that I just would like to see things better, and but I can't quantify just one thing, without going back in time. So as dumb as that sounds, that's where I sit. So the guy in Ohio, one of his that Drag Nova, that's one of them. Yes. Yeah. So the Blue Nova with twin turbos. Yes. So that's a funny story. It's now single turbo. We're redoing it. The turbos were too big for the transmission brake system on it. So if you look at a lot of the really expensive drag cars, they have trans brakes, but they also have dump valves. The dump valves drop the line pressure and allow the engine to spin more freely, more like a clutched-in manual car. Not that much, but better. And it makes it easier to get to your target RPM without having to pull through the converter and without raising trans temp too much. Well, he didn't have the dump valve. He only had the trans brake. And so the RPMs were really hard to push up to get the turbos to spool, and took a long time, and he hit the train up a ton just in one pull. So we added some nitrous to get the spool faster, but still it's dragging through all that pressure in the converter and everything. So he's getting the dump valve put in the transmission. We're going to one turbo so we get faster spool out of that because he doesn't need 1800 horsepower. We set it for like 1800 and then found out that was twice the horsepower we needed to turn the time that car is certified for. So why have that much turbo and that much power if we can't even utilize it without getting kicked off the track? So we're going to one turbo that's a couple hundred horsepower larger than our target, so that it's an efficient setup. It's going to be less laggy than the two turbos, and then also the engine got hurt. There was a miscommunication between he and I in that. I kept telling him that we need to do these things, and I didn't portray them enough, and he had a misunderstanding about how the systems worked. So it ended up running lean on cylinder 1 and breaking the plug, which then banged the piston and the head up a little bit on cylinder 1. So he's fixing that right now too. And yeah, so lesson learned for both of us. I should be more assertive and explain better why I want to do the things I want to do, and he'll understand that, you know, more about ignition advance and per cylinder fueling and how that goes. He had some misconceptions about that, and so we spent a lot of time talking about that. So he'll be more knowledgeable and more appreciative of that stuff, and I'll be better at portraying what I think needs to happen. So that's where that went. I'm somewhat scared of where the automotive industry is going. I really don't like to see. Yeah, the EPA is fucked up right now, man. No shit, the EPA is just way fucked up. They're definitely intruding on us, and I've said it 100 times on stream before, because we're just a bunch of single people, little single entities around that can't get together very well. I mean, we try and get together with SEMA, but even the SEMA organization only has so much power, and we don't have the strength of the billions that the transportation industries and all the industries and power industries and all those other people that pollute like crazy. So like there's a lot of industries that pollute that just have lawyers, banks of them standing by to fuck with the EPA, or they've got money and they're paying off people in the EPA. So there's money from these companies going towards politicians to shoot down stuff that would affect their industries, where with us we don't have that. We don't have that going on. So we're easy. Yeah, exactly. We're too easy to pick out. Absolutely. We're easy targets, especially when they attack one tuner at a time. They just do this one little here, and like they have all the people lined up. They just got them on fucking queue, right? And they just attack one at a time, and then ones at the bottom of the list get scared and fucking back out anyways, and then they just slowly just chip away at the industry, just like gun control, just like your health, just like all your license and permits. They just chip away at you, and until the new normal is the new jail, or the new jail becomes the new normal, and then they make the cell smaller and make the cell smaller and the cell smaller, and it's just kind of the way it's going, unfortunately. So yeah, we're definitely easy to pick on, and we're really easy to demonize, right? Because we're polluters for the environment. We don't care. We're that kind of stuff. They make us evil people in the eyes of other politicians and other organizations and the public and that kind of stuff. So that makes it really easy to single us out and to minimize the amount of support that we can get. Oh, well, the cars are loud. I saw a thing in the EPA. The EPA has a thing, and it says the only reason that people put louder mufflers on their cars is to scare and intimidate other people. I shit you not. It's on the fucking EPA website. The only reason we put mufflers on our cars that are louder is to scare and intimidate other drivers. That's what it says. It's asinine. But that's the kind of shit that goes on, with our government. Yeah, that's the only reason. Yeah, absolutely. It's on the website, dude. I had to dig for it. I was going through some shit one day, and I saw that in some papers. I was like, what the fuck? Yeah, it was insane. It was like one of the directors of the EPA said it, and it's on their website, and I found it also in a document. Oh man, it actually was barely related, but it popped up. I was doing some papers, or doing some research on papers, and that one popped up. But yeah, just look it up. Only reason for mufflers is scaring. I bet you if you put that in, just those boards in Google, it probably would come up with the stuff. But yeah, that's the only reason. It's only to scare and intimidate people. I heard this thing misfire once. I bet we're running low. Let's see where our fuel pressure is. Ethanol temperature 48.6 Celsius. That's hot. pressure is still, it's a little low. The difference pressure is a smidge low, and the temperature is a smidge high. And by smidge, I mean it's a lot high. So yeah, I gotta cool that fuel down and add some more. This says cranking table, which I really thought was the cranking timing, but it might be a trim table. They tell us it's cranking time, but it might be a trim to the ignition table. The ignition table is 18, and the log showed I was cranking at 17. And if you look at my cranking table, where do you go? Whoops. Look at the cranking table. Where do you go? It was 1 to 2. So is this retard or is this advanced? I don't know now. So now let's do this. Let's just make it let's make it 5. And I'm going to save that. And I'm going to crank on it and see what the cranking timing is. .5. Okay. Where's my primary table at? I thought I had that on here. Maybe I took it off. Transient, limits, idle, scatter, mixture, starting. EDT. So that was 20 degrees. And we were here at 18. Wait, let's go back. Yeah, right there. So tuning engine. So I was there at 18. It was giving me 20.5. I have a degree yanked off of it for charge temp. Mission trims total 2. Mission cranking trim 5. See, it is a trim. It says it's a 5 trim. But it says the total trims is 2. I mean, it starts good like that. I like how fast it starts, but that doesn't seem the way that the table is supposed to be used. It doesn't look like the way the table is labeled. But oops, wrong one. That table. Now I'm confused. Give it a name. It's not the base map anymore. Sure, idle's good. Happy with that, I tell you. Gotta shake that knob a bunch. Let's see. 120 degrees. That's right when fuel starts to boil in these things. save. Good. And that's saved there too. Alright, that's it for today. I'm going to add some fuel, check the oil leak, and, well, what I assume is an oil leak, and see about some more stuff. Maybe investigate the boost control some more, figure out why we're getting 25 on the gate, and go from there. So, hey, I appreciate you guys actually asking questions and getting to talk to me a little bit and hanging out. I appreciate you guys. I hope you all have a wonderful weekend. It's Friday, so happy weekend to all y'all. And I start school again Monday. I finish up with this semester coming up. I will finish up my math degree, and I am my second semester into computer science. So that'll bring me to 4 little degrees, and then working on my 5th one to be computer science. So I'm having a good time with that. I'm learning a lot with programming. I'm excited for that because I have some things that I want to create that require some programming, and I'm excited for being able to do that. So hopefully some new products in the future, a couple years from now, but I think they'll be really neat, and for the computer science stuff. And then I have other stuff in the works right now, just trying to get the R&D cash saved up so that I can pay for the tooling too, or the production cash saved up to pay for the tooling to get those other products made. So yeah, then hopefully I get some more stuff done. Hope material costs come down, because material costs make everything impossible. There's a New Year's wish for 2023. I hope material costs go down. All right, y'all. Have a good weekend.